So last time we talked about building an 8-bit adder, correct? In the last lesson, we studied about building 8-bit full adder. We first built 1-bit adder, and then we just chained 8 bits one after another, and we built an 8-bit adder. So today we will learn about some tips and tricks, what else we can do with an 8-bit adder. Well, the first thing that we can do with an 8-bit adder is obviously adding two numbers together, right? So we use adder to perform instruction, which we will call add. So add, you just give two numbers to 8-bit adder, and it adds these numbers together and gives you the sum of the addition. Now let's look at the following thing. Let's say we have an 8-bit system, so 8-bit microcontroller or 8-bit processor. But what if we need to add two 16-bit numbers or maybe two 32-bit numbers? I'll show you it with an example. Let's say we want to add two numbers in decimal. For example, 37,999 plus, let's see, 1 second. So I'll convert them to binary immediately. So, and in binary, this number will be 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1, 1, 1. And the second number will be the following. So, in binary. I'll write it in binary and then convert to decimal. So we would have a more interesting example. So the other number will be 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0. For example, this number. I'll convert it now from binary to decimal using Windows calculator. 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0. So this number is 15,000, 0, 82. 15,082. So can we use an 8-bit adder to add two 16-bit numbers? So we have, bottom 8 bits and top 8 bits for each number. So let's see, how would we add decimal numbers? So 9 plus 2 is 11. 9, this is 18. This is 7 and 5, 12, plus 1, 13. And here we would have 3 and 1 is 4, 5. So we should get 53,081. Okay. You would probably guess that regardless of the size of the number, all we need to do is just add carry, bit A and bit B. you know, and we can do it within all of this number, regardless of how many bits there are. And let's check out. So first, when we add two numbers, the first bits, we always assume that carry in is 0, right? So we add, you know, computer only has this 8-bit adder that accepts A, B, and carry in. So we need to give it some carry in initially. So when we add first, you know, bottom part of the 16-bit number, we give carry in equal to 0. Okay, so let's perform 8-bit addition with our 8-bit microcontroller on the 16-bit numbers. So first 0 plus 1 plus 0 is 1, and the carry is 0. 0 plus 1 is 0, but carry is 1. 1 plus 1 plus 0 is 0, but carry is 1. 1 plus 1 plus 1 is 1, and carry is also 1. 1 and 0, 0 is 1, and carry is 0. 0 plus 1 is 0, and carry is 1. 1 plus 1 is 1, and carry is also 1. And here, 1 plus 0 plus 1 is 0, but carry is 1. So in this moment, all we need to do is somehow pass this carry from bottom 8 bits to top 8 bits when we add. Because if we simply add bottom 8 bits and then top 8 bits, also assuming carry in 0, we will have a mistake here. So we need to pass this carry equal to 1 from bottom 8 bits to top 8 bits. And in 8-bit system, we cannot pass it directly. That's not how processors are built. But what processors do have is something called status register, short for SREG. I'll write it with text. Status register. And it is a special small memory cell in which some bits between operations are stored. And one of such bits is carry bit or carry flag. These status registers, its contents are often called also flags. So one of the flags inside the status register is C flag. Maybe I'll write it with text. So basically, when we do any kind of arithmetic function in the processor, almost always there's a possibility that a carry will be produced. For example, we added these two numbers. We had in bottom 8 bits, we had overflow, so we have carry. And the processors are built in such a way that this carry is sent to status registers, bit C, which is carry bit, and it's stored there. And then when we want to add the top 8 bits, we don't use function add, we use another instruction, which is called ADC. And this translates to add with carry. So what this thing does is it takes the carry, so we stored this one, it takes carry from status register and inputs it in our 8-bit adder initially. So when we do add, we assume that carry in is 0, but when we do ADC, add with carry, the carry is taken from status register and given to our 8-bit adder, and now we will have a correct result. So 1 plus 0 plus 0 is 1, 0 plus 1, and the carry is 0. 0, 0, 1 is 1, carry is 0. Here we will have 0, 1, 0 will be 1, carry 0. Same 1, carry 0, 1 and 1 is 0 and carry 1. Same here. And like this. And now we can check out if the result is correct. So I'll use this Microsoft calculator for conversion. So binary 1, 1, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1. So this number indeed is 53,081. Okay, so if we simply added bottom 8 bits and then top 8 bits and always assume that carry in for 8-bit addition is 0, we would have made a mistake here and we would have a result which is 256 less than the real result. And the carry between 8-bit operations is stored in this status register C bit or C flag. Just for your information, status register holds other flags as well, one of which is half carry. So I don't know if it's used in modern computers, but originally many systems were using binary coded decimal system where numbers were stored like decimal numbers. You know, for example, you want to store a number 458, then this 8 would be stored in 4 bits. So 8 is 1, 0, 0, 0. So this would be stored in one 4-bit location. This 5 would be stored as 0, 1, 0, 1 in another location, and this 4 would be 0, 1, 0, 0 in another location. And in this binary coded decimal, you cannot have numbers larger than 9. So when the result is greater than 9, then you would have to add whatever is on top to the next position. But generally, this binary code decimal, I think it's still built into the architecture of controllers, but it's not really used. But for some operations, it also had this overflow between bottom 4 bits to top 4 bits. So for example, if you added like this 458 plus, I don't know, 3, you would add them together, you would have overflow to next bits. So there was something called half carry bit H. So this status register can also hold this H bit or H flag. I'll just write it because it's also in the test. So in the processors, there is this half carry flag, which is carry from 3rd bit to 4th bit. So when we do 8-bit addition, for example, we had, when we added bottom 4 bits, we had carry, then this would go to H flag. And as I mentioned before, you will probably never use it, but you know, it's built in historically. So this overflow from third bit to fourth bit is stored in half carry flag in status register. Status register is, for example, in 8-bit system, it is an 8-bit register. In ARM controllers, in 32-bit systems, everything is 32 bits, so it's also 32 bits. In the processor that we will be building in our labs, it will be simple 8-bit memory cell or 8-bit register. So there, you know, 2 of these bits are a carry flag and half carry flag. And then we will learn about some other flags as well. Okay, so do you understand why we have add and add with carry instructions? Is it clear? You can write in chat or answer with your voice. Okay, seems like everybody understands more or less. So, you know, I can just write with text. So to add, for example, 16-bit number on 8-bit system, add bottom 8 bits with add, then top 8 bits with ADC. And of course, this applies to 32-bit systems and 64-bit systems. Even on 64-bit processors, if you want to add 128-bit numbers, you know, for some scientific things, it's the same. So to add 128-bit numbers on, for example, 64-bit Intel or ARM or Apple M1 chips, it's the same. You will add bottom 64 bits with add, and then top 64 bits with ADC. And, you know, to expand it further, you can also run 32-bit code on 8-bit processors. So to add 32-bit numbers on 8-bit system, add bottom 8 bits with add, then next, second, third, and fourth bits with add with carry. So, you know, if you had 32-bit number, then you add only bottom part with add, and then the next, second, third, and fourth part with add with carry so that you don't lose it. Okay, so pretty simple. Okay, so if this is clear, let's look at the next thing, which will be negative numbers. Okay. I will delete all of this. And let's talk negative numbers. Okay. I'll rewrite that later. So negative numbers in binary systems. So negative numbers in processors are stored in the following way. So originally, negative numbers were stored, you know, in the first iteration of computers, they were stored in the following way. So let's say you have a number 5 which in binary is 0, 1, 0, 1 in, in 4 bits. I'll just write in 4 bits. So if you want to write -5, you would just, the agreement would be that we sacrifice the top bit for sign, and we just set it 1 if it's negative, and then we write the number the same. So 1, 0, 1, it's 1, 2, 4, so 4 and 1 is 5. So this is 5, and this is plus sign, and this is minus sign, right? So -5 like this. And obviously what you would notice is that, let's talk smaller systems, for example, a 4-bit system. In 4-bit system, how many combinations can we have? How many numbers can we store? How many different numbers can we store in 4 bits? So it's, each bit can be either 0 or 1. So it's 2 times 2 times 2 times 2, or is the same as 2 to the power of 4 equals to 16. So obviously we can store numbers from 0 to 15. If we didn't have zeros, then it would be from 1 to 16, but since we can store 0, so it's 0 to 15, 16 different numbers. So whenever we introduce a sign, we of course lose 1 bit on the sign. So with negative numbers, in this case, we only have 3 bits for, the base number, and one of the bits, the 4th bit, is used for sign. So in this case, we can have, so 2 to the power of 3 equals to 8 different numbers. So it's from 0 to 7. But plus or minus, so it's plus or minus 8. So it's still 16 combinations, just from from -7 to +7. So let's see, from -7 to +7. But how many different combinations are there really? From -7 to 0, it is 8, but then 0 is already used. So from 1 to 7, it's only 15 combinations. Because the problem with this notation is if you write 0, 0, 0, 0, it is like +0. And if you write 1, 0, 0, 0, it is -0. So the fallacy of this method of writing negative numbers is first that we have plus and minus zeros. And it is bad, we don't want to waste memory on storing the same number in 2 different ways. So this method of writing numbers, not very great, but for the sake of simplicity, whatever, we can make some hardware stuff that when all bits are 0, we also enforce the top bit to be 0, and that's it. Another problem is this. Let's say we want to add 5 plus -5. We expect the result to be equal to 0, right? So let's try to add them. 0, 1, 0, 1, plus 1, 1, 0, 1. If we add them, 1 and 1 is 10. Here is 1. And here is like this. Okay, let's say carry is overflow. We throw it in the trash and we add the signs, I don't know, in a different way. But generally, we see that we have gotten a wrong result. So 0, 1, 0 is something like 2. you know, and maybe sign will be +2, maybe it will be -2, but, you know, we got the wrong result. So in this case, what we would have to do is we would have to build some kind of system where we first check the bits. So if we add positive and positive number, then we can use addition. When we add negative and negative, we can also add them together because the sign will not change. But if we have positive and negative number, we need to make another block which would do subtraction. You know, perform an instruction which we will call subtract. And how we could do it, we could write all possible A, B, and carry in combinations for each position, just like we did for an adder, and then derive what is Q and what is carry out, right? And it's possible, and first processors really had it, right? And then, depending on the sign, we would switch between add and sub, right? So if we add two positive numbers, we add. If we add positive and negative, we actually need to subtract them. Also, if we subtract from positive number a negative number, we would also actually select addition. And if we subtract positive from positive, then we use sub. And it all becomes really complicated and hard to follow through. So, and also because people are lazy, they figured out that maybe they should, instead of trying to build a subtraction block, they would do some tricks and, you know, avoid it entirely. Because subtraction isn't really that simple. For example, for me, it's really hard to subtract numbers because, you know, instead of adding to the next position, you have to borrow from next position. And how do you do that? What if it's 0 already in that position? I don't know. Subtraction is pretty complicated. If I subtract two positive numbers, let's say 100 minus 5, for example. 0 minus 5, okay, we have to borrow 1, so I'll write -1. 0 minus 5, I borrow 1, so it's 10 minus 5 is 5. Here, 0 minus 5, actually, I would have to write the carry, not on top, but maybe even on the bottom, so -1. Here, so 0 minus 1, which we borrowed from the previous position, we again have to borrow, and 0 minus 1 is 9. And yeah, I again wrote it in the wrong position. This 1 minus 1 is 0. Okay, so we could calculate this, but how do we calculate, you know, 5 minus 9? How do we do that? There's nothing to borrow from. So, you know, I don't like subtraction even on decimal numbers, let alone on binary. So people figured out that they can actually avoid subtraction altogether if they change the way that the negative numbers are represented in the processor. And check it out. So they decided to use this, you know, base assumption. So base assumption for generating negative numbers in such a way that we can avoid all the subtraction nonsense is A plus minus A has to be equal to 0. If we construct the negative numbers in such a way that we add negative number bits to positive number bits of the same value, of the same magnitude, and we get 0, then everything is great, right? And so they figured out that to calculate a negative number, we just have to subtract the positive number from zeros. So basically, minus a equals to 0 minus a. And you would say, wow, what an arithmetic. But the trick is that, let's say we have 8-bit system, you know, we can also write it as a hidden 1 in front of the 0 bits, and then we will get an A. So actually, what people decided to do to construct these numbers, instead of A plus minus A equal to 0, it can also equal to 0 plus carry out from the top position. And with an example, it would be like this. If you add A plus minus A, you can get zeros and carry out. So actually, it becomes easy to convert to negative number with the following formula. So minus A equals 2 to the power of n, which is, you know, the number of bits in your system, minus A. Because we can store in 8 bits only numbers from 0 to 256, which is, 255, the 256 looks like this, 1 and then 8 zeros. So if we add two numbers from which the negative number was derived by subtracting it from 256, all the bits will be zeros. Yes, there will be carry out set, but let's say we discard it. We don't care about it. And in that case, this is how we can get a negative number. And I'll try to show it to you with an example. So let's say we have number, I don't know, let's use the same 5, right? How do we get minus 5? So what we want to do is we want to, oh yes, and 5 in 8-bit system, for example, will be 0, 0, 0, 0, 0, 1, 0, 1. This is 5. And we want to create a negative minus 5 in such way that when we add the negative minus 5 to plus 5, we get zeros. So minus 5. So to get minus 5, what we can do is subtract from 1, 0, 0, 0, 0, 0, 0, 0, 0, which is 256, which is 2 to the power of n in our system. We can subtract the 5. So 0, 0, 0, 0, 0, 1, 0, 1. So when we add them together, we will get actually 256, but all the bits will be 0. So 0 minus 1, we need to borrow minus 1 from next position. 0 minus 1 is 1. 0 minus 1, which is carry, is again 1. And we borrow from the next position. So 0 minus 1 and minus 1 is like minus 2. Minus 2 is 0 and carry to the next position. Minus 1, 0 minus 1 is -1. So the carry for the next position is also -1. And actually it will give all ones here because it's the same thing. And then this top one -1 + 1 is 0. So actually 5 will be written like this. We get it by subtracting +5 from 2 to the power of n, and we get this number. And now we can compare if we add, oh yeah, and this is carry out. So 8 bits. Now let's check out if we got the numbers right. So the idea is we get -5 in such a way that when we add it to +5, we get 0. So let's try to do it. So 5 is 0, 0, 0, 0, 0, 1, 0, 1. So this is +5. Let's add them together. So 1 + 1 is 10. 1 + 1 is 10. 1 + 1 is 10. 1 + 1 is 0 and carry 1. 1 + 1 is 0 and carry 1. 0 and carry 1. 0 and carry 1. And 0 and carry out is 1. So we got all zeros when we added this +5, which is real 5, with this strange -5. We got zeros. Yes, the carry out was 1, but if we ignore it, everything is fine. And this is how numbers are represented in the processor in this special way. And also, let's look at this number from the positive perspective. Let's say that this number is not negative. Let's say it's a positive number. So if we convert it from binary to decimal, what we will have is 1, 1, 1, 1, 1, 0, 1, 1. And in decimal, it is 251. So the math is correct. 256 minus 5 is 251. And so 251, you can represent as a positive number 251, or it is also virtual -5 in this special notation. So this arithmetic works. And maybe you're a bit confused about this carry. We discard it, maybe you don't like it, but that's how we can avoid subtractions if we represent negative numbers in this special format. And this special format is called 2's complement. Either it's written 2's complement or also 2's complement with words. Why it's called complement, 2's complement, it means that this -a complements this +a in such a way that when you add them together, you get something whole. You get zeros or you get 2 to the power of n, it's the same thing. So this is the arithmetic of 2's complement. And so we can convert numbers to 2's complement in 3 ways. And one of which is you take to derive -a, you perform 2 to the power of n minus a, and you can do it in decimal and then convert to binary, or you can do it in binary if you like it, and you get the number. One cool thing about 2's complement format is negative numbers still have 1 in front. The most significant bit, the 7th bit in 8-bit system, is 1. So we can use it as sign flag. So this top bit is sign. And also we only have 1 0. So all zeros is 0. And 1 0 0 0 0 is something else. Of course, if we are using 1 bit for sign, then when we're using numbers in 2's complement, of course, we get combinations only from minus 128 to 127. So how do we get this 127? Very simple. We write the largest positive number that we can imagine, but only in 7 bits. Because the 8th bit in front is 0, so that it's positive number. So this is 127 and 0 in front, so it's plus 127. And minus 127 will actually be 1 0 0 0 0 0 0 0. Because you have to add 128 to get all zeros. You can do it in your head, you know. To get 0, you have to add plus 128, which would be 1 0 0 0 0 0 0 0. And then all zeros yield zeros, and 1 plus 1 is 0, and carry is 1. So all bits will be 0. So this is how you can remember it. Okay, so let's convert a couple of numbers. But maybe I'll teach you some other stuff first. So I'll save it. Delete some of this. This. Okay, so 3 ways to convert from positive to negative numbers. First was 2 to the power of n minus a. Okay, so I did it with 5. So, you know, let's do it with 5 again. So 5 was 0, 0, 0, 0, 0, 1, 0, 1. And minus 5, in this way, we obtained 1, 1, 0, 1, 1, 1, 1, 1. I guess it was something like this. 1 and 1 is 10. 1 is 10. Okay. The second way to convert from positive to negative numbers in computers is this. Invert all bits and add 1. Flip all bits, then add 1. Let's try it out. So 5. Let's flip all bits. Okay, I'll write it once more. 0, 0, 0, 0, 0, 1, 0, 1. Invert all bits. So 0, 1, 0, 1, 0, 0, 0, 0. And then add 1. And it is 0 plus 1 is 1. Then 1 plus 0 is 1, 0, Oh, sorry, I didn't invert the bits. I didn't invert all bits like this. So flip all bits to the opposite value and then add 1. So 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. And then 1, 1, 1, 1, 1. Okay, and we got the same result as here, right? So this is the second way to convert from positive to negative numbers. Invert all bits and then add 1 and you get the result. And the third way is starting from the right, copy all bits as they are until first one. Copy it as well, and then invert all other bits to the left. So starting from the right, copy all bits as they are until you meet first bit, which is 1. Copy that one as well, but then invert all other bits to the left. So let's try to do this. So plus 5 is 0, 0, 0, 0, 0, 1, 0, 1. Copy all bits from right as they are until you meet first one. Well, the first bit is already 1, so I have met 1. I copy it as it is, but the rest of the bits I invert. So 0 becomes 1, 1 becomes 0, 0 becomes 1, 1, 1, 1, 1. And again, we got the same result. So there are 3 ways, 3 methods to calculate 2's complement from the original number. One is you subtract it from 2 to the power of n. Second is flip all bits, then add 1. And the third one is starting from the right, copy all bits as they are until you meet 1. Copy that one without change as well, and then invert all other bits. Is it clear how to convert from normal numbers to 2's complement? You can write it in the chat. Okay. And now I'll just talk about the ranges of numbers again. So in, let's say in 8-bit system, but you'll figure it out for higher bit systems as well. In 8-bit systems, 2 to the power of 8 is 256. So we have 256 combinations. For unsigned numbers, you get from 0 to 255. For signed numbers, you get from minus 128 to 127 values that you can store. And for higher bit systems, it also applies. So this is in general 2 to the power of n minus 1, and this is 2 to the power of n minus 1 because 0 is positive, so it grabs from the positive number pool. So obviously you get less possibilities. And some people get confused. How does the computer know if we're working with signed or unsigned numbers? Actually, the computer doesn't know. So it's up to your code to define variables in, for example, C programming language as signed or unsigned, depending on your application. So the computer doesn't really know. It just adds bits and that's it. So you have to remember that, for example, if you're working with signed numbers, which go from, for example, from -200 to +800, you cannot use 8-bit number. You need to use, for example, 16-bit number. The computer doesn't know it. Okay, so this is the way how we can convert numbers. Now, question to you. Please write in the chat, everybody, which is the easiest method for a human to convert from positive to negative numbers? First, second, or third? Which is the easiest and fastest for human to do? Well, for a long time, the second was my favorite. But actually, you know, if I give you a large number, maybe a 64-bit number, to convert from positive to negative, you know, maybe it's faster to just copy bits until 1, then copy it and then invert other bits. You know, you have to remember to do it, but if you learn it, maybe the third one would be the fastest. Second is also pretty fast, but you know, you need to do 2 operations, invert and then add. Maybe I'll try to use a different number. Okay, so for example, number 32. Let's do a quick conversion. 32 equals to 32 equals to 0, 0, 1, 0, 0, 0, 0, 0. So if I use this third method, I can just copy bits 0, 0, 0, 0, 0. Okay, here I made the first one, I copy it, and the next bits I flip, right? So this would be -32. If I did it in the second method, I first need to invert all bits. 1, 1, 1, 1, 1, 0, 1, 1. And then I need to add 1. And I'm going to have quite a bit overflows. 1 and 1 is 10. 1 and 1 is 10. Like in binary, 10. So 1 and 1 is 0, carry 1, 0, carry 1, carry 1, 1 and 1, 0 is 1, and then 1, 1. Okay, I got the same result, but it kind of took me more effort. So, you know, maybe it's better to memorize the third one. It's like instant for a human. Now in the chat, right? But of course, it's your choice. If you like subtractions, you can use the first one as well. Tell me which one would be easiest to implement in hardware to teach a computer. So which one would be easiest for a computer to do, easiest to implement in hardware, in your opinion? First, second, or third? You can also make a guess. This is not a graded question. Third, okay, somebody says third. First, Some other guesses? So, what logic elements did we study in our first lessons or in the second lesson? We studied not, which is inverting a bit, you know, calculating the opposite bit. And then in the next lesson, we built an adder, which can add 2 numbers. So my guess, and also Alex's guess, is that you can flip all bits and then use our 8-bit adder to add 1. So maybe that would be the easiest one. So in reality, unless you want to build a subtractor or some crazy logic, which kind of tries to, you know, detect ones, well, if you're doing it as a stream, then of course the third one is also pretty simple, right? But if you want to do all of this in parallel, then the second one would be better for computers. So in computer, you just calculate, you know, you flip all bits and then you use an 8-bit adder to add one, right? So the second method is basically A with stripe above it plus 1 equals minus A, right? So, you know, for computers, maybe the second one is best. So after all of this intro, you know, with all this math, basically what I wanted to tell you is that we can do some neat things with our 8-bit adder. Here's addition. And I'm going to show you some tricks, and I hope you will be amazed by what an 8-bit adder can do. So I'm going to delete all of this, not necessary anymore. So let's call it multi-purpose 8-bit adder. So I will draw a table and we will fill it with some interesting stuff. Let's see. So I'll tell you in advance that we can actually do 8 different instructions with our 8-bit adder. Let's see, how will I name them? Done. So divide by half, 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 and half, and like this. And we will fill this interesting table. So I already told you that we can do addition with our 8-bit adder. So instruction name will be add. And what we will have as input will be some modified version of A, B, and carry in. So when we want to add two numbers, A and B, we simply take A plus B and we set carry in to 0. Carry in is equal to 0. And when we want to add top parts of some larger number, we use add with carry instruction, ADC, and we take A, B, and we use carry from status register. So I'll call it C, you know, carry. We will build the processor in such a way that we can feed carry from status register, or we can also select 0. Next thing that we can do is, in very many processors, you often have to increment some counter. For example, you write a loop, for example, for I equal to 0, I smaller than 5, I plus plus. So to perform this plus plus without using a second number, which stores and holds just number 1 inside, it's built in hardware in processor that you can select an instruction which simply adds 1 to A. So we will call this instruction int, like increment. We take A, but instead of using B, we will enforce number 1 and carry in 0. So this instruction is actually built into practically all processors, because the processor builders know that you often use a counter where you increment something. So increment is A plus 1 plus 0. So B will not be used in this case. B will stay untouched. Also, oftentimes you want to do a minus minus or decrement operation to decrement a number. And the instruction name is det. And in this case, we take number A, but instead of 1, we need to give -1. And we will give it in 2's complement format. So we can use our adder. So we will do -1 equals 2, 0, x, ff. So maybe you know it, but -1 is all ones. So I'll write it here. -1, regardless of the number of bits you're counting, is all ones. Equals to 0, b, 1, 1, and so on, 1, equals to, in hexadecimal, 0, x, f, and on so on, f. We can, you can use, like, if you, in 8-bit system, you write 1. And for example, with this system where you copy all bits until you meet first 1, and then invert all other bits after 1, it doesn't matter how wide the registers are. It doesn't matter if it's 64 or 8-bit system. This yields all ones. So in our hardware, we can just simply select A as the one input and then feed all bits high to generate this -1. And of course, carry will be 0. And this way we get, so A -1, If you take a number and add all ones to it, it will result in something decreased by 1. Okay, so next thing that we want to do with our 8-bit adder documents, let's see, I will write it in the order of lab work. I guess it was this, yes. So first was add with carry, increment, decrement. And the next one will be okay. The next one will be calculating a negative number from a positive number. Let's see. Instruction set manual. Yes, the name is neg. So instruction name will be neg, and it is negative. Please return negative number from the positive number. Again, this will only use one input, A. We give it A, and we want to receive -A as a result. So this neg calculates -A. And as we talked about previously, calculating -A is simply inverting all bits in A and adding 1 and carry in 0. So if we give our 8-bit adder A with all bits inverted, so first, instead of giving directly A, we switch to A passed through the NOT gates of each bit. Each bit passed through a NOT gate. We get inverted all bits, and then we add 1, we will get -A in 2's complement format. So neg will give us this. And the next thing is subtract. So now we get to the real deal. How do we add, how do we use 8-bit adders to subtract numbers? Let's see. How much is A minus B? So A minus B is equal to A plus minus B, which is equal to A plus, and minus B is B with all bits inverted plus 1, right? So what we can do is to perform subtraction, we give our 8-bit adder A, then we give our adder B with all bits inverted, and for carry, we just enforce it equal to 1. Okay, and this way we can use 8-bit adder with just some NOT gates in front of B to subtract numbers, and we don't have to build a subtractor. We don't have to switch between additions and subtractions depending on the signs of the number. And we saved a lot of time and also a lot of space in our CPU because we have the same 8-bit adder that performs subtractions. And there's also subtraction with carry. So when you subtract two numbers, it's possible that you have an underflow. So what we had was when we subtracted any bit position, so I don't know, 1, 0, 1, 0, 1, 1, 1, 1. I don't know, let's subtract these numbers. So, okay, I'll put 0 in front so we don't have some crazy thing. But generally, and I actually will move this line and I'll write carry down so it's a little bit easier. So initially carry is 0, so 0 minus 1 and 0 is we need to borrow. So 10, which is 2, 2 minus 1 is 1. 1, when we subtract from 1, another one is 0. 0 minus 1 is minus 1, which is we need to borrow from next position. And then we add 1, minus 1, 0, minus 1 is minus 1. And borrowed, 0 minus 1 is minus 1. So 10 minus 1 is 1, minus 1 is 0. And here 1 minus 1 is 0. But anyway, let's say we had 2-bit system where we had only a 2-bit adder. When we subtract these numbers, we have underflow, which passes to the next part of the number. So we first subtract first 2 bits, then we subtract the next 2 bits. So again, we can throw this carry or borrow in status register. And then when we want to subtract the next part, we take it back and use it. So again, for subtraction, just like for addition, if we add or subtract big numbers greater than what our bit width allows, we first do add or subtract. And after that, we do add with carry or SBC, subtract with carry. So what we do now is we take, okay, let's try this subtract with carry. So subtract with carry would mean A minus B. If we had overflow, also minus carry. So we subtracted bottom part A minus B of some big number. We got some result. Maybe the bottom part was larger than the top part. So we had underflow. So we need to borrow from the next position. So we need to subtract the carry. So we get A minus B minus carry. And let's convert this as well. So A minus B minus carry is A plus minus B minus carry equals to A plus all bits of B inverted plus 1 minus carry. So this part is minus B. But check it out. If we rearrange something, A is A, B with all bits inverted is B with all bits inverted, but how much is 1 minus C? If you really think about it, because our adder only accepts 3 inputs, A, B, and carry in. Here we have 4 terms, A, B with bits inverted, 1, and C. So we would have to squeeze this 1 somewhere in the middle, but we don't want to do it. Let's turn our brains on and figure out if this means something. Let's say carry is 0 or carry is 1. So 1 minus 0 equals, so 1 minus 0 is 1. 1 minus 1 is 0. So 1 minus carry is equal to the opposite of carry. So carry was 0. The result 1 minus 0 will be 1. So it's the opposite of what the carry was. And 1 minus 1 is 0. It's the opposite of the carry value. So 1 minus carry is exactly equal to carry inverted. So we get A plus B with all bits inverted plus carry with its bit inverted, right? So instead of taking carry, we just pass it through a NOT gate, and then we put the result into this adder. So in our table, we have A, B with stripe, and carry also with a stripe with bits inverted. So we still are using the same 8-bit adder. We just change what we feed into it, modify, but we can use the same building block to get the result. So these are the 7 functions that we can do. And there's one more extra function that we can tell our 8-bit adder to do. It's a little bit, out of this world, but it is mov. Copying value from one register to another. So one way to copy values would be to copy from register to register somehow, but actually, since we have covered all arithmetic things that we want to do with our processors, 8-bit adder, and we have still one combination free from 8, everything is binary in computers. So we can use adder to copy value from B to A in some special way, which we will study a little bit later. But generally, if you select A equal to 0 and B equal, just B, and carry equal to 0, and then you tell the result to be written to A, what you get is A equals 0 plus B equals B. So, 8-bit adder is this 8-bit adder is somewhere in the processor, and it takes values from memory. And you can select which memories to read from and which memory cell to write to. So we can use adder, for example, to select write to A equals 2. And if you want to copy B, it's 0 plus B. It's just B. And so we can use this arithmetic logic unit to copy value from B to A. Okay, so you can remember it. If you wonder how, we can copy memories in very, very simple systems, cheap processors, it's done through arithmetic logic unit. You just calculate a 0 plus B, you get result and write it back to memory A location. In modern processors, there's some hardware acceleration where you can copy masses of memories from one place to another through a separate peripheral, which is called DMA, direct memory access peripheral. But you know, it's complicated. In our simple processor, and also historically in some old processors, it can be done this way. So to copy value B to A, you can use arithmetic logic unit, add 0 to B, and write result to A, and you get the result. So this is how we can use our simple 8-bit adder to do 8 different things. Okay, so now you can write in chat if you understood everything. And what do you think about it? Is it good or is it bad? Okay, so one person understood everything. Okay, so yeah, what I just wanted to show you is people use processors because they are simple, not because they're complicated. If processors were complicated, they would be much more expensive and we wouldn't be able to afford to put a processor inside every home appliance. You know, initially people used relays and some mechanical systems to control some process. Today, because processors are so simple, it's just easier to throw in a processor in a microcontroller and write some C code than to try to build everything mechanically. And it's all thanks to people trying to do things simply. So with simple 8-bit adder, which consisted, as you remember, just from 448 transistors, we could build thing that does 8 different functions: adds, increments, decrements, subtracts, calculates negative number. You know, calculating negative is the same as multiplying with -1, for example. So in your code, in your C code, if you calculate something like, I don't know, x equals -y, it doesn't take millions of years to calculate -y. You just do it with one simple instruction in your arithmetic logic unit in your 8-bit adder, right? Okay, so that's about it. Not so much time. I'll save this. And there are a few other flags in status register that I have to mention to you. See, how do we detect overflow of negative number addition? Let's say we want to calculate -1, -1, right? So it is -1 plus -1. And -1, as I mentioned you, is all ones. So it's 1, 1, 1, 1. I write it in 4-bit system because it doesn't matter how many bits we have. And let's add them together. 1 plus 1 is 0 and 1. 1 plus 1 plus 1 is 1, 1. 1 plus 1 plus 1 is 1 and 1. 1 plus 1 plus 1 is 1 and 1. As you can see, let's convert this result first. We have 1, 1, 1, 0 and carry out. So when we added positive numbers, if we had carry out, we knew we had overflow, right? A mistake, you know, you added 2 big numbers, they didn't fit in a resulting register, so you had overflow. So it's a problem. But here, let's see what this number is. Let's convert it to positive numbers. So copy all bits as they are until you meet first one, and then invert all bits. So 0, 0, 1, 0. This is 2 to the power of 1. This is 2. So basically, this is equal to 2. So if this is 2, this is minus 2. And we added minus 1 equals minus 2. So result is correct, but carry out is set. So we had virtual overflow, but the carry was set. So carry bit C cannot be used to detect overflow of negative numbers or negative number operations, right? Let's see what flag can be used. Let's add minus 128 minus 1. So as I mentioned before, minus 128 is the largest number that we can write in 8 bits. And, you know, let's also subtract minus 1. Let's check it out. So minus 128 is 1, 0, 0, 0, 0, 0, 0, 0, plus, and minus 1 is all ones. So 0 and 1 is 1, 1, 1, 1, 1, 1, 1, and 1 plus 1 is 0, and carry out is 1. But the carry from previous positions was always 0. And so what people detected is when you add two negative numbers, carry out and carry to previous position, if they are the same, there's no overflow. If you added positive numbers, they would both be zeros. If you added two negative numbers, they're both ones. But if you added numbers in such way that you have underflow, then these bits from previous position and from last position are different. So there is this V flag, which is equal to carry out XOR carry, I'll write carry 7, you know, this carry 7. If they are equal, if they're the same, there's no overflow. So this V flag will be equal to 0. But if they are different, then we have overflow. So this V flag also resides in status register, and it is used for signed overflow detection. Well, of course, you should always write a code that doesn't have overflows, because you write C programming. In C programming language, you don't really work with these status registers. This is maybe a little bit from older days, but generally, V signed overflow flag is there, and it can be also sometimes used for some comparisons or for some branches. But generally, this is what you have to kind of, you can remember if you want to. And you will actually build it in labs, so you'll remember it. So carry flag is overflow, V flag is signed overflow. If you are adding two negative numbers, you need to check it instead of carry. And two more flags. Oftentimes you write if, right? In your C programming language, if, for example, A equals B. How does computer know if two numbers are the same? Basically, it subtracts one from another, A minus B. It calculates A minus B and checks out if the result is 0. So status register also holds a 0 flag, which is if result of all bits is 0, then this flag is 1. So it is all bits ANDed. So bit 0 and bit, or all of them inverted and then ANDed. So B inverted and B 1 inverted and B bit 2 inverted and so on, and bit N inverted. So if all bits are 0, then all of them inverted will be 1, and then you AND them all together and you get 0 flag. And it's probably actually all bits NOR, because if you write inversion on top of it and break all of these lines, you will get, I think you get NOR. So actually 0 flag is also all bits NORed. So 0 flag in status register is 1 if result was 0, and is 0 if result was 1. So after doing arithmetic functions, the status register is updated. And another flag is the following. You write, for example, if A smaller than B, then do something. How does the computer know if A is smaller than B? It calculates A minus B, and then it checks the negativity bit, the top bit of your number, to see if it was negative. If it is 1, then the result was negative, and you know this is true, and it will do something that you tell it. Right, but if this top bit is 0, then the result was positive, so A was larger than B, right? So there's also this N flag in status register, just the most significant bit in result, right? So it just checks out the most significant bit and stores it in status register. So our status register has flags carry, signed overflow, 0, negativity, and as I mentioned on older systems, it also holds half carry. I don't know why it's still there, but it's used. And also status register oftentimes holds something called I, or interrupt flag, which enables or disables interrupts in CPU. We'll study about interrupts, of course, much later. We're still at the arithmetic part of the processor, but I think I have a test. And in the test, there is a question about these flags, and you have to, but you can Google the meanings of the flags if you want to. And then fill the test based on that. But generally, the status register holds some number of flags, some of which are carry, signed overflow, 0, negative, half carry, and also interrupt enable flag. Okay, so, and don't worry, in labs, you will build a status register. So if you didn't get it now, you will understand it when you build it, right? Okay, do you have some questions? We're almost out of time. So if you don't have any questions anymore, then I will tell you what you need to do. Let's share this screen. So in Ortus, right? What I hope you have done is you have watched the video lecture from this, from first and second week. Then I hope you also did the homework, the design of logic gates. You can do it pretty easily if you search on the internet some circuits, and then you kind of verify that the circuit is correct. And also, I have translated the test number 1 to English, so you can fill it. It's actually pretty simple. I don't know, let's see. It's just 10 questions. You can do it unlimited number of times. The only limitation is it closes at the end of I think this week. So you have to do it now. Why? Because students are lazy. If they have deadlines, they do things, but if they don't do anything. So, you know, so that you don't have everything left for the end of semester, I will put deadlines on tasks so you keep yourselves disciplined. So here are some questions in the test. You can do the test unlimited number of times. In this test, there are only 10 questions, but the answers and the questions will be randomly, you know, mixed, so you don't memorize them. The goal of the tests is for you to learn. This is why you can do it in unlimited number of times. It's not a punishment. The test is not a punishment for your ignorance or stupidity or lack of studying. It's for you to learn. You do it, you didn't get some questions right, you study it, you Google it, and then fill it again until you get 100% correct. So the test is translated. Also, after last week's video lecture, you can do homework number 2. It's very simple, just conversions between bases. But I want you to do this homework on paper and make a photo of that paper with your handwriting, filling, you know, calculating these tasks, and put that in Ortus, you know, because if you do it in Word, then maybe one person does it and then gives to everybody else. But if you do it on paper with your hand, I see that it's not the same work. And also you can do test number 2. I have translated it. This test is a little bit more complicated because it has a bank of 17 questions, but only 10 questions, randomly selected 10 questions will appear. And next time you do the test, new questions appear randomly. So it's a little bit harder, but still you can do it unlimited number of times. But the deadline is, let's see, 2 weeks from now, 10 of October. 10 of October, almost midnight, 59. Okay, so this is the deadline for this test. Okay, homework, I think I already had deadline. And finally, oh, for this homework, the deadline is next Monday. But you'll do it. It's pretty simple. Don't procrastinate. And now I want you to also do lab number 1. If you haven't done it yet, you can do lab number 1 and lab number 2. Okay, here's something wrong, but lab number 2, you can do it. Lab number 2 is precisely about what we did this lesson. You will take your 8-bit adder and then you will build some logic gates in such a way that you can select between addition with carry, subtraction, increment, decrement. So it's really, really interesting stuff to do. So please do everything, including lab number 2. The next things you don't have to watch. The next things we will do in the next lessons. So please do everything. And of course, I will set some deadline. Let's see. So that you have motivation to do it. The deadline will again be 10 of October, but I expect you to do it for the next lesson. Okay, if somebody did some homeworks already, of course, you don't need to redo them. If somebody, for example, took homework number 2 then spend 5 hours typing in formulas in Word, you don't have to delete the Word document and do it on paper. You can hand it in as is. But I have a good memory, so if I see two people having identical works, then I will divide the mark by 2. You know, 2 people do the work, they get half of salary each because it's the same work. Okay, so do everything up to lab number 2. Okay, that's all for today. And we meet after 1 week. Okay.